Okay. So first, I will get your second exams back on Wednesday. So I'll have those back to you. And then the biggest thing going on right now is this week is lab exam 2. Before I get into new material, does anybody have any questions related to labs that you'd like me to answer? Any questions that as you were studying for that stuff, you had questions about? Okay. So it's not going to have any of what was the last thing we did? The Newton's third law. It's not going to have any of the stuff related to Newton's third law, but all of the stuff before that.
Like the turning?
Like what?
The turning?
Yes, exactly. Like two-dimensional accelerations, interpreting position versus time graphs, vector addition, that stuff is all.
So when you do the adding or subtracting vectors,
yeah.
You know, you do the dotted line, does it matter where you put the arrow on each end?
Okay, yes, vector addition. So if you're going, let me just make two. Let's say this is the vector A, and this is the vector B. And let's say that let's do A plus B. And then let's do negative A minus B. And then let's do 2A minus 3B. 2A minus 3B. Okay, so to add two vectors, you start at some point. I guess I can do this. So take one of the vectors, and remember, order doesn't matter, so you can choose either one. This might be more trouble than it's worth. So you start at a point, you follow from that point to some intermediate point with one of those vectors. Then from there, you take the other vector, and what you have after you do that is a starting point and an ending point, and then that intermediate point with both vectors at it. And the actual answer for the sum of two vectors is just the vector going from the starting point to the ending point. So this is the answer to adding those two vectors. This was A, this was B, and this is A plus B.
It doesn't matter where you put
where I put which thing?
Like
the head?
Yeah, the head.
Okay, yeah, I mean, it has to be, if you put the head on the other side of the red vector.
That's okay, it doesn't matter.
No, it does matter. It has to be this way because it has to be an arrow that goes from the starting point to the ending point.
Got it.
Okay, so if you put it on the other side of that red vector, you'd be going from the ending point to the starting point. So that'd be like the reverse of the answer. Okay, and then if you're doing A minus B, so always think of the negatives as first you're multiplying by -1, and then you're adding. Okay, so negative A would be, so we still have a starting point like that. You'd follow negative A to get to there. Then you'd follow negative B, which is like that. And the answer to this, so again, you have a starting point and an ending point, and so the vector has to go from the starting point to the ending point. Okay? And 2a minus 3b, well, think of first coming up with a vector that's 2 times a, second coming up with a vector that's negative 3 times b, and then adding those two vectors. So 2 times a would be in the same direction, but twice as long, you know? So, whoops. So this is 2a. And then negative 3b would be in the opposite direction of b and 3 times as long. So that's negative 3b. And so then 2a plus this negative 3b, which is means the same thing as minus 3b. You'd start at a starting point. You'd take that vector 2a. From that intermediate point, you'd take that vector negative 3b. Yeah. So this is negative 3b. This is positive 2a. And this is 2a minus 3b. Okay? Anybody have any questions about that? And just remember that when we talk about adding vectors where we know the directions but don't know the magnitudes, we come up with that range of directions. And it all does come from vector addition like this. You know, that's how you would like show how you get the answer. But if, let's say you had m times a plus n times b, and m and n are unknown positive numbers. For that, you don't think of it as a trip. You think of it as like hands of a clock. So there's the center of the clock. You have one vector in the direction of A. You have one vector in the direction of B. And the answer could be any of these directions in between. Okay? Any other lab-related questions?
If you last lab worksheet, you have copies on D2L?
Yes, on D2L. Yep. Yeah, you can just print it off. Anything else? Okay. And then any homework questions, homework problems you want me to go over? All right. So now we're going on to the next topic. And this is conservation laws. There are two conservation laws we're going to deal with. So first of all, like, what does that mean, a conservation law? Conservation means a quantity that doesn't change over time. You've probably heard of conservation of energy. That means that in the universe, there's a certain amount of energy. It's not being added or subtracted. It's just changing forms. And that's a sort of a fundamental law of science. One of the conservation laws we're going to deal with is kind of a special case of conservation of energy. But anytime you find something you can measure that no matter what happens as this motion takes place, that quantity stays the same, that's a conservation law. So the two that we're going to be dealing with are conservation of linear momentum and we haven't talked yet about what linear momentum is, but we have to define that and stuff. But this is useful in certain cases. With any physics equation, like half of the difficulty is figuring out when that equation applies. Conservation of linear momentum, we're only going to use that for collisions. You can also use it for explosions. We're just going to deal with collisions. So this is a really nice one in the sense that you always will know in this class whether it's the right time to use this equation. If you're dealing with a collision, then you're going to use this. If you're not dealing with a collision, you're not going to use that, and that's the end of it. Okay? This is a pretty easy one to use in the way that we're going to use it, and so we're not going to spend a ton of time on this. And then the second one is conservation of mechanical energy. This is a special case of conservation of energy. Conservation of energy always holds. There are no counterexamples where it doesn't work. In certain cases, this simplifies to special case of conservation of mechanical energy. And this one's a little more complicated. We're going to spend a bit more time on this one. Okay, so we're going to start with conservation of linear momentum. And it's very simple to know whether to use this. If a problem involves a collision or an explosion, although I don't think any of the problems I'm going to give you involve explosions, you'll use conservation of linear momentum for at least part of this problem. Okay, so the first thing we have to do is define linear momentum. So let's say the linear momentum of an object. People denote it with lowercase p, and it's a vector. I don't know where the p comes from. I think it's actually from Latin or something. People have been using that forever. But the definition of linear momentum is the mass of an object times its velocity vector. So this is the velocity vector of the object's center of mass. The SI units for momentum are kilogram meters per second, which you can just get straight from that definition. And there are a couple of things I want you to notice. The first one is that linear momentum is a vector. So it not only has a magnitude, it has a direction. And the second thing about it is the magnitude of the momentum. You can think of it as telling you something about how hard it would be to stop an object. Okay. So how hard the object would be to stop. So, for example, a ladybug has very little momentum. A train that's going full speed has a lot of momentum. If you had to choose which one of those you wanted to stop, you'd choose the ladybug. Okay. So conservation. Let's. So let's say you have a car with 1,000 kilograms of mass moving at 40 meters per second. How fast would a 50 kilogram person have to move to have the same magnitude of momentum? Okay, well, the car we're just calculating the magnitude of the momentum. We're not worrying about the fact that it's a vector for now. Has a mass of 1,000. Times a speed of 40 meters per second. And so you get 40,000 kilogram meters per second. Okay. So now if the magnitude of the person is going to be equal to that same amount, that would have to be equal to the mass. Well, it's going to have to be equal to some speed that we're going to calculate. Times 50. And so, what's that going to be? 8. The speed would have to be I think that's 8,000 meters per second. Is that right? 40,000 divided by 50. That's 4,000 divided by 5. 800. Yeah. Thank you. Okay, so conservation of linear momentum. You can't apply this all the time, but here's what it says. Choose a set of objects that might make contact with each other but have no net force applied by the surroundings. Okay, so they could be smashing into each other, applying big forces to each other, but as long as you're including all those objects that are running into each other in your system, all that matters is what the stuff outside your system is doing. There can be no net force. There can be forces, but those forces have to add up to 0. Okay? Then conservation of linear momentum says the mass of the first object times its velocity vector plus the mass of the second object times its velocity vector, plus so on. Let's say there's n of these. And this is at instant 1. Has to be equal to the sum of the momentums after at instant 2. Nope. So m1 times v1 plus m2 times v2 plus till you get to mn times vn at instant 2. There are a few things to notice about this. These are things that you definitely want to remember. The first one is you want to choose a view and therefore a coordinate system where the net force from the surroundings is 0. Remember that a view from above often works because you don't have to worry about gravity. Okay, so if something's in free fall, or if multiple objects are in free fall, is there a net force on those objects? Yeah, gravity is acting on them. But if you take a view of those objects from above and do all your calculations in a coordinate system using that view, then you can forget about gravity because it's not showing up in your calculations. This isn't always true, but it's often something to think about. What else was I going to do? What else was I going to say? I know one more thing. Conservation of linear momentum isn't enough to determine final velocities by itself. You need information about the type of collision. So say you have two objects and you know the masses of the two objects. Say one's 1 kilogram and this is 2 kilograms, and you know the velocities of things before they collide with each other, okay? What are the velocities going to be after the collision is over? Well, intuitively, it makes sense that you need to know more than that. Like, what if these two masses are pieces of clay? Then they're going to run into each other and stick together and sort of fall down to the ground, But what if they're pool balls? Then they're going to bounce apart and the velocities are going to be totally different. So conservation of linear momentum is something that can help you find velocities after a collision, but you need more information than that. And then the third thing is, in this definition here of conservation of linear momentum, I have instant 1 and instant 2. When we use this for collisions, instant 1 will always be right before the collision. And instant 2 will be right after the collision. Okay, so let me show you an example. showing that conservation of linear momentum by itself isn't enough. Okay, so let's say we have these two train cars. Maybe that's a bus, I don't know. And let's say this one's going this way along the tracks. At 20 meters per second. And this one's going this way along the tracks at 10 meters per second. And this one's 5,000 kilograms. And this one's 10,000 kilograms. What are the velocity vectors of each cart? This really should be is, by the way. What is the velocity vector of each cart after the collision? Well, our system is going to be the two carts. Is there any external net force on this system? So they're obviously going to smash into each other and apply a lot of force to each other. But is there going to be any other force besides that contact force? There is gravity. But think about the directions of, so it's moving in a straight line, right? And so gravity is acting down, but there's not going to be any vertical acceleration because it's moving in a straight line. So if you calculated the net force on these, ignoring the contact force, there's no net force because there's no acceleration. Okay, so there's no net external force on the cars. So conservation of linear momentum applies. Before the collision, let's calculate the total linear momentum. So the total linear momentum, and I'm going to use a coordinate system like the one we're used to, like this. Okay, so for the 5,000 kilogram cart, is that velocity, that 20 meter per second velocity in the positive x, positive y, negative y direction? Positive, so this is going to be 20, 0. And then the linear momentum for the other one is going to be a mass of 10,000. Times the velocity vector of this. What's the velocity vector of the 10,000 before the collision?
-10.
Yeah, exactly. -10 in x, 0 for y.
Does that just add to 0?
What?
Does that just add to 0?
Which one?
The whole thing.
You're right. It is going to add to 0. I didn't mean to do that. Thank you. Okay, so this is going to come out to be 0, 0. Okay, this doesn't have to be 0. I should have chosen different numbers. Doesn't have to be 0, but it is in this case. What? happened? So this doesn't have to be 0. It just happens to be in this case. Okay. Well, after the collision, all of the following satisfy conservation of linear momentum. The velocity of the 5,000 and the velocity of the 10,000 are both at rest. Because you'd have 5,000 times 0, 0 plus 10,000 times 0, 0 is equal to zeros. So this would work. Another thing that would work would be the velocity of the 5,000 is equal to minus 20, 0. And the velocity of the 10,000 is equal to positive 10, 0.
I thought the 20 was going in the opposite direction.
Before it was, but I'm just sort of making up some numbers that satisfy this equation, you know what I mean? So all I'm trying to show here is, like, without more information, this can't tell you how fast they're going after the collision. Do you know what I mean? So these are like possible velocities after the collision.
What other information would you need?
You need to know something about what kind of collision it is. Like, are they going to stick together? Are they going to bounce apart? To what extent are they going to bounce? That kind of thing. Okay? So 5,000 times negative 20, 0 plus 10,000 times 10, 0. And that gives you 0, 0 again. Okay? And I could come up with infinitely many combinations of velocities that would satisfy this. Okay? What I'm getting at here is there's no unique answer. Without more information about the type of collision. Okay. So if these things bounced apart, they'd have some kind of set of velocities. If they stuck together, they'd have some kind of velocities. If they were halfway in between those, they'd have some kind of velocities. So what kind of problems are we going to work on? In this class, we'll only do inelastic collisions. That's the easiest type to do. So we'll get the sort of intuition about how this works without getting too bogged down in complicated math. What this means is that after the collision, the objects have the same velocity. They stick together. Okay. So what this says is you'll have one mass times its velocity vector plus another mass times its velocity vector however many bodies you have, usually we'll just have two, times the last mass plus the last mass times its velocity vector. And that's equal to the sum of all the masses times Vx, Vy. Okay, so let's do an example. Let's do basically the same thing again. Let's use numbers where it won't come out to be 0. So let's say we have a 2,000 kilogram object that initially is rolling at 3 meters per second. And a 4,000 kilogram object that's initially at rest. If the cars latch together when they collide, what's their velocity vector after the collision? Okay, so this fact that I gave you that they latch together when they collide, that's giving you that extra bit of information about the type of collision that's going to let us calculate this. Okay, so we'll start by coming up with the total momentum before the collision. So first think, is there any external net force on this system? Is anything applying a net force to these besides the collision with each other? Nope, so we can use this. So before the collision, we have 2,000 kilograms times the vector positive 3, 0. After the other object before the collision, 4,000 kilograms. Its velocity, it's at rest. So its velocity before the collision is 0, 0. After the collision, we have, you can think of it as like a single object now that has a mass of 6,000. And we're going to calculate the two velocity components. This 6,000 is just the sum of the masses. Our x equation says 2,000 times 3 is 6,000. 4,000 times 0 is 0. This is equal to 6,000 Vx. And so Vx is equal to 1. The y equation says 2,000 times 0 plus 4,000 times 0 is equal to 6,000 times 0, so that's not helpful. I'm getting ahead of myself here. This is equal to 6,000 Vy. So Vy is equal to 0. And so after the collision, the velocity vector of that whole system is positive 1, 0. Or in other words, it's moving in this direction at 1 meter per second. Any questions about that? Okay, let's think about another one. Another example. So let's say that you have a ball that's moving horizontally at the instant that a kid catches it, and it's moving horizontally at 5 meters per second. And the kid that catches it is on a skateboard. His giant arms, E.T. Freak show. It is E.T. And let's say that this kid has a mass of 20 kilograms, and the ball has a mass of half a kilogram. And let's say the kid on the skateboard is moving at 1 meter per second before the collision. What's the velocity vector of the kid and the ball system and skateboard after he catches it? Well, think about this for a second. Is there any external net force acting on this system?
Is there a normal force acting on the skateboard?
So there is, and there's also weight forces acting on stuff. So you probably don't have to think about this because I'm going to tend to give you problems that you can do this using this approach. But it's a good habit to get into to think about, the net external force before you go into this. Well, remember that there can be forces on an object and still not be a net force if they add up to 0. In this case, though, there's no net force, no net external force on the kid because there's a gravity force and a normal force, like you said. But there is a net force on the ball. So in this view, we actually can't use conservation of linear momentum, but we can take a top view and do it because then the weight force acts into the page. Are you with me on that? And the normal force acts out of the page. Everything's, you can just ignore it. So I'm going to take a top view. And it looks like this then. Something like that, you know. The ball's coming this way. The kid's coming this way. Now, if our coordinate system is this, there's no net force in this coordinate system, so we can use conservation of linear momentum. So let's see, before the collision, the ball has a mass of 0.5 kilogram, and it's moving at +5 in the x, 0 in the y. And then the kid has a mass of 20 kilograms. And before the collision, he's moving in the negative x direction. And this is equal to the total mass. So if you add up the two masses, you get 20.5 times the velocity vector, x and y components. So the x equation says 2.5 minus 20 is equal to 20.5 Vx. And the y equation says 0 plus 0 is equal to 20.5 Vy. So this says negative 17.5 is equal to 20.5 Vx. So can someone divide negative 17.5 by 20.5?
Negative 0.854.
Negative 0.854. The y equation says Vy is equal to 0. And so the velocity vector after the collision is negative 0.854, 0 for y. Or in other words, the system is moving this direction, the direction the kid was moving before, just a little bit slower now, 0.854 meters per second to the left. Any questions about that? As an aside, we're not doing any calculations with things that bounce apart, but does anyone have a feel for what if this kid didn't catch this ball? Do you think if the ball hit the kid's hands and bounced back in the direction it came, do you think the kid would be slowed down more or slowed down less by a ball that bounces off his hands?
Slow down less.
It does sort of seem intuitive, doesn't it? But in fact, actually, the kid will be slowed down more if the ball bounces off. And it makes sense if you think about the fact that, remember, the momentums of the two objects after the collision have to equal the momentums before the collision, okay? So think about the momentum of the ball. In in the case that he catches it, the ball is moving with the same velocity as the kid. In the case that it bounces off, it's moving faster in the other direction. And so the kid's momentum has to make up for that extra momentum of the ball, and the kid would actually be moving, would be slowed down more in this case. Okay, that's not really important, but it's sort of interesting. Let me give you a problem. Do we have time? Yeah. Let's just do a quick problem. So let's say that two cars collide. This one has a mass of 1,000 kilograms, and at the instant they collide, it's moving 10 meters per second. And this one has a mass of 1,200 kilograms, 1,200 kilograms. And it's moving this direction at 12 meters per second. If the cars stick together in the collision, what's their velocity vector after the collision?